The most important thing to remember when you're calculating ion molarity using Solute math is always, before you get caught up in doing any kind of calculations, write a balanced equation for the dissolution of your ionic compound in aqueous solution. So we know this VBr3 doesn't really exist like that, right? We write it as a molecule that's undissociated with the symbol AQ, but for a soluble ionic compound, that is a lie, because what we actually have is we have vanadium, in this case 3 plus ions, AQ. How did I work that out? Because there's 3 bromide ions and bromine has a -1 charge, so it has to be vanadium 3, right? We already covered this. Okay, and then that is going to yield 3 bromide ions, AQ. Okay, so this is what we really have in that solution. So always write out a balanced chemical equation first. We're asked to calculate the molarity of the bromide ions in our solution. So you can write a mole ratio. Okay, so the number of moles of undissociated vanadium 3 bromide is that every 1 mole of vanadium 3 bromide is going to yield 3 moles of bromide ions. So do that before you even look at any numbers. Okay, yes, I know there's numbers in there, but you know what I mean, right? We're looking at the stoichiometry. Okay, so then what we have to do is we've been given the mass in grams of the vanadium 3 bromide, and we've been given the volume of the solution. Well, guess what? We don't need that until right at the end, okay, when we're calculating the concentration of the bromide ion. So just ignore that for a minute. All we need is this 21.5 milligrams of vanadium bromide, because we're going to convert from our mass in milligrams to our mass in grams. And then you guessed it, we're going to get our moles of vanadium bromide. And this is where it starts to be really important to write moles of what, because we're going to be converting from moles of, I guess, our reactant, vanadium bromide, to moles of our product, which is the bromide ions. And so we need a mole ratio between them. And then we're going to divide by the volume to get to our concentration of bromide ions. So a lot of people get excited about the numbers and doing, moles divided by volume to get concentration. They forget this one crucial step, which is using the mole ratio from your balanced chemical equation. So before I get into that, I guess I should work out the molar mass of vanadium 3 bromide, sorry, my bad. So vanadium is, I think, 50, I can't read it. Is that 58? I'm going to have to zoom in. I don't really want to do this. 50.942. I guess it's a good job I checked. So vanadium 3 bromide is 50.942 plus 3 bromines. Bromine is 79.904. All right, what does that give you then? Let's find out. We'll ask Mr. Calculator. All right, 50.942 plus 3 times 79.904 gives me 290.654 grams per mole. Okay, so let's do it then. And we know the prefix milli is 10 to the -3. Okay, so mass in milligrams was 21.5 milligrams. Convert mass in milligrams to mass in grams. 1 milligram equals 10 to the -3 grams. All right, so we got rid of milligrams, and then we know that 1 mole of vanadium 3 bromide, yep, steady on there, weighs exactly, whenever I just calculated, 290.654 grams. Sweet. So as of this point, milligrams cancels, grams cancelled. I've got my moles of vanadium bromide, so I need my moles of bromide ion. So I'm going to stick that mole ratio in there. 1 mole of vanadium 3 bromide yields 1 to 3 moles of bromide ions. All right, nearly there. So then we just need to get our concentration of bromide ions. The volume is 50 milliliters. I know concentration is in units of moles per liter, so I've got to sort that out. I've got to change milliliters into liters. SI unit prefixes, 1 milliliter is 10 to the -3 liters. So just stick that in there. Bob's your uncle, right? There we go. Right, so do cancel, cancel. Moles of vanadium 3 bromide cancel. That's why it's always important to write moles of what? Okay, and then my milliliters cancel. Give me units of moles per liter, which is concentration of the bromide ion. So 21.5 times 10 to the power of -3 divided by 290.654 times 3 divided by 50 divided by 10 to the power of -3. Hopefully I used my calculator correct. I got 0.00443822 blah blah blah. Right, so we're asked two significant digits, which will be here. Okay, and I should probably give it in standard scientific notation. So I'm going to say 4.4 times 10 to the power of -3, and that is in molarity. Okay, same thing. All right, so I guess I can show another just to make sure we know what we're doing. Okay, basically the same thing. Okay, this time it's with iron 3 chloride. You know what? Let's not do that one because it's the same ratio. That's kind of boring. Potassium chloride is just 1:1. I guess that's what we're going with. Oh, okay, we'll do KBr then. Okay, so just to be clear, even if it's 1:1, you still should be writing this out and converting the units. So KBr AQ will break apart into K plus ions, AQ, and what is it, bromide, Br minus AQ. Okay, so for every 1 mole of KBr that dissolves, you get 1 mole of what we asked about, bromide ions. Okay, so it's a 1:1 ratio, but you should still do all these steps. Okay, potassium bromide, let's get at the periodic table real quick. Potassium is 39.098. Jeezy crazy, 39.098. Bromide is 79.904. So potassium bromide is 119 point something. Okay, so for every 1 mole of KBr, that weighs 119.002 grams. So get your equivalencies together. So we want to convert that 0.90 grams, so mass in grams, to the moles. Be specific, moles of KBr. Then we can convert that to the moles of bromide ions. And then if we got the moles of bromide ions, we can divide by the volume in liters to get to the concentration in moles per milliliter. Okay. So we're going to get moles per milliliter, and then we'll end up with moles per liter if we use the conversion between milliliters and liters. Okay, so mass in grams was 0.90 grams. Number of moles per, mass in grams per mole is 119.002 grams for every 1 mole KBr. So notice that I'm still including my mole ratio. Okay, so for every 1 mole of potassium bromide that dissolves, it yields 1 mole of bromide anions. So mathematically that doesn't change anything, but look at how the units are still changing. Okay, so then the concentration is going to be, we're going to divide through by the volume, which is 300 milliliters. So right now I've got a concentration, but it's in moles per milliliter. Not really what we want. So I'm going to have to convert milliliters into liters. Yes, you could do this in a separate step, but then you could make a transcription error. You could accidentally times by something when you meant to divide by something. It's much safer to include it all in the same working so you can verify that your units are cancelling out appropriately, and you end up with the number that you are expecting in the desired unit. So grams cancels out, moles of potassium bromide cancel out, milliliters cancels out. My answer is going to be moles per liter, which is my definition of molarity. So 0.9 divided by 119.002 times 1 divided by 300 divided by 10 to the power of -3. So it's so important to still follow through this method, include mole ratios, write that balanced equation so you have it, etc. Okay, so just going to write M per molarity. We're asked for two significant digits, which would be this. So in scientific notation, that's going to be 2.5 times 10 to the power of -2 molarity. All right, that'll do. Have some practice with that.